we can see that there are intricacies in the solution of the Navier-Stokes equations, and it is not easy to get a solution in a very straightforward way. We have to do something more in order to squeeze out a solution using the conventional CFD method for the generic scalar transport equation. We have seen two methods, the artificial compressibility method and the stream function vorticity method, for the solution of all the four equations that appear in the Navier-Stokes equation. Both the methods have limitations. Now we look at one method which has no such limitations. It can be applied for time dependent flows in order to get a time accurate evaluation of UVP W as a function of xyzt, and it can also be used for 3-dimensional flows. So it is a method which is applicable for fully 3-dimensional transient flows. So the method that we are referring to is what is known as the pressure equation method. We know that we can solve the momentum equations provided we know what the pressure is. Now we do not know what the pressure is, we have to get it from the continuity equation, and for incompressible flows pressure is not there as a variable in the continuity equation. So that is where we have tried to eliminate pressure in the stream function vorticity method, or we have introduced surreptitiously the pressure in the form of artificial compressibility in the other method. Now what we do is that now we will try to solve the momentum equations along with the Poisson equation for pressure that we have derived earlier. Now we will put it in the general 3-dimensional context, and then we will see how we can evaluate both of these step by step in such a way that we get a velocity and pressure field which together obey the Navier-Stokes equations without the attendant limitations of either the artificial compressibility method or the stream function vorticity method. So the idea is that we write down the momentum equations, we derive the equation for the pressure, and then we try to come up with an algorithm by which we can implement the solution of these two equations together. So that is what we will do. We will call this as pressure equation approach. For simplicity we will use the index notation to write down the momentum equations. Dou ui by dou xj of uiuj, understood that there is a summation convention employed here, 1 by rho dou p by dou xi plus nu del square ui by this. We have left out gravity, it is not a big problem, so we will just use these equations. These are the equations, the three momentum equations, and we have dou ui by dou xi equal to 0 as the continuity equation. So these are the equations that we want to solve, and this is the generic scalar transport equation, and we can solve this provided we have the pressure. And what we try to do is that we take the divergence of this, okay, that is we take, if you call this as equation A and equation B here, then we take dou by dou xi of A, given that in each term there is an I which is appearing here, so that we are effectively taking the divergence, and we can show that in this particular case when we take the divergence for incompressible flow with constant properties and with the continuity equation, we can get an expression for okay, essentially this is nothing but the Laplacian of the pressure. So this is equal to minus 2 rho let me see if this is correct. This must be there is a rho term in this. Let me just verify if this is the case. Yes. So this is the Poisson equation for pressure, and this, as we have mentioned earlier, we have written down the two-dimensional form of this in the stream function Wurtz-City method, and this can be solved provided the right hand side of the Poisson equation is known. So one idea would be to solve this with an assumed pressure and get the velocities, put the velocities here, get the pressure, and then use this pressure to go back and calculate this, and then get a velocity field. We can do this kind of iteration. So that is one way of solving this. Okay, an easier probably way of implementing this for an explicit when we consider an explicit solution of the Navier-Stokes equation for a time accurate method is something that can be done in a simpler way like this. Let us consider an explicit method. Okay, so now we consider we know that we have the advection term and we have the diffusion term and all these things, and we can rewrite this as minus and so we have the left hand side term and then we have the right hand side terms involving the spatial derivatives. Out of this we have, if we did not have this, then it would be straightforward to evaluate this because that has only the velocity components. Now what we say is that this is determined explicitly, so we can write down from this, for the sake of nothing, without losing any generality, we can take the density here, we can make this dynamic viscosity, and we can put density here. And although we are dealing with incompressible flow, we have to remember the incompressibility is something that is coming from the pressure versus velocity relation, for example, as encapsulated in the Bernoulli's equation. We can have other reasons for density variation which is not part of the incompressible flow assumption. For example, you can have air at say 1 atmosphere pressure, and it may be that you have a reaction which is going on because of which for example oxygen is absorbed and then carbon dioxide is released. So you can have the composition of the air, the gaseous medium, is changing from location to location, and as the composition changes the density changes. So that kind of variation is not part of the incompressible flow assumption. Okay, so that is why there is one reason to put rho inside here, because that takes care of those kind of situations where density variation is not arising from the compressibility considerations but from other considerations such as compositional changes. So we can put it down without loss of generality, without affecting the assumptions that we have made in terms of incompressible flow and the time step limitations for stability and all that. So we put it like this, and we can make use of a discretization, and we can say that rho ui n plus 1 minus rho ui n is equal to delta t times, we can call this as delta p by delta in an explicit method. So, this is evaluated at nth time step using some discretization, so that we are replacing the partial derivative with respect with delta to indicate that this is a discretized part. We are not specifying what the discretization is, that is immaterial to this as of now, plus u times del square ui by del xj okay. So, this is a discretization in an explicit way of the momentum equation, so that we can get rho ui at n plus 1 from known values of the pressure gradient at the nth time step, and the discretization of this all evaluated at nth time step. Okay. So, this method can be used provided we know this. Now, what we want to do is that, because pressure and velocities are not known readily, we have to make sure that we put the correct pressure gradient in evaluating this. So, we want to make sure that the pressure gradient is evaluated, or the pressure is evaluated properly at the nth time step, so that using this discretization for the momentum equation will give us the correct value of velocity at n plus 1. Okay. So, we want to make sure that in solving this, in using this explicit method to go from ui to ui n plus 1, we put the correct pressure gradient here at n. So, the evaluation of pressure is now posed in a different way, okay, is posed in such a way that when we put that pressure gradient at nth time step in this discretized equation, we get the correct evaluation of ui n plus 1. Okay. Now, what is meant by correct evaluation? So, that velocity is satisfying the momentum equation, the discretized momentum equation, but it also has to satisfy the discretized continuity equation at n plus 1. Okay. So, we say that the pressure field, the pressure evaluation at n must be such that the evaluated velocity at n plus 1 must satisfy the continuity equation. Now, what is the continuity equation? It is dou ui by dou xi equal to 0. So, in a discretized form is equal to 0. So, the n plus n is equal to 0, and similarly n plus 1 is equal to 0. So, so this must also be equal to 0. Okay. So, if we can impose this condition in evaluating the pressure gradient at n, then we can make sure that we have the correct velocity field here. Okay. So, now we have to get an expression for this. So, what we do is we take the divergence of this, just as we have taken the divergence dou by dou xi of this, we can take the divergence of the discretized equation, and therefore we can say that rho ui at n plus 1 that is the divergence of the first term minus dou by dou xi of rho ui at n is equal to delta dou by dou xi of that is the this one plus delta t, and we have mu here coming from this, and then we have dou by dou xi of this. Okay, if you now take it inside, okay, let me just put this. And then we have finally this one. Let us see, this is square brackets, so we will just put this as this. Okay, so this is the divergence of the discretized equation, and we have to put the correct indices. This is n here and here, and this is n and n. This whole thing is evaluated essentially by making use of the n values for this. Okay, so now here we can impose a condition that this is 0 for continuity. Okay, so this term must be 0, and this is a condition that we want to apply here. So we say that for the velocity field at ui n plus 1 to satisfy this, then the divergence of the equation that we are, the divergence of the discretized equation must be such that this term is 0. Okay, and this term is anyway 0 because the velocity at nth time stage should be satisfying the continuity. Otherwise we can also make we can include this. So we have this condition here. Okay, so provided the pressure gradient at n plus 1 is such that the divergence of the pressure gradient, okay, is equal to the divergence of the viscous term and the advection term here, then in which case we will have continuity equation, okay, continuity equation being satisfied by ui n plus 1 obtained from the momentum equation. Okay, so the argument that we are saying is that we have the momentum equation, and this allows us to calculate the velocity at n plus 1 by discretizing it appropriately in a way that we choose. And for this equation to satisfy the continuity equation, okay, the computed velocity at n plus 1 to satisfy the continuity equation, we have to evaluate the pressure gradient, the pressure at n in such a way that this satisfies this equation. Okay, so it satisfies if we say that this there is a minus sign somewhere. Okay, if this is equal to okay, so if we evaluate pressure from this, okay, and use that pressure to evaluate the pressure gradient here, which is then used to evaluate the ui n plus 1, then we have the guarantee that the momentum equation is being satisfied by the ui n plus 1, and also the continuity is being satisfied by the velocity field that is predicted. So we are enforcing the condition of satisfaction of continuity by choosing to evaluate pressure gradient such that it satisfies the continuity. Okay, so in that sense we are choosing a pressure field, a P ijk at nth value, the previous step value, to be evaluated from the previous values of the velocity field. See, on the right hand side here we have only the velocities that are appearing and the velocities at nth time step, which are known, okay, either from initial conditions or somehow. So if you know the velocity field, then we can make use of the known velocity field to get a pressure field at nth time step, which when substituted into the explicit form of the momentum equation will enable us to calculate a velocity field at n+1 which satisfies the continuity equation. Okay, so this is the basis for the pressure equation method in the explicit way. So we start with ui. So for example uvw at n equal to 0, this is the initial time, that is part of the specification of the boundary initial conditions. So that is known. So once this is known, then we use that to evaluate the right hand side of, if we call this as okay, so we have equation A here, and then we have equation B and equation C, and we can see that this equation and this equation are similar. This term will go to 0, and then we will have only that one. So this is dou by dou xi dou by dou xj of rho ui j, and that is exactly what we have here. Okay, in a discretized form there may be some leftover term, so this term is expected to be very small, but we are enforcing that won't create any problem. Okay, so we have equation C here, and this is, let us call this as equation D. And this is our equation E, and this is equation F, and finally we have the equation G here. Okay, so we are making use of the pressure gradient obtained from equation G to substitute in this in order to get a velocity field ui n+1 from known velocities. So from known velocities at nth time step, we evaluate the pressure at nth time step such that it satisfies the continuity equation, and then using the pressure evaluated from this Poisson equation, we evaluate the pressure gradient here, and then we substitute in this and calculate ui n+1. So that is the method that we can use for this. So use equation G to get Pn, okay, and use equation D to get ui n+1. So those are the three ways. So with this, now you can go to use equation G to get P n+1. From this, instead of n, we make use of the velocity field at n+1. So, and now we can go to the n plus equation D to get u n+2, ui n+2, and then equation G here to get Pi n+2, and so on. Okay, so we evaluate a pressure here from a known velocity field, subject to the condition that the evaluated pressure when put in the momentum equation will give us a velocity at n+1th time step which satisfies the continuity equation. So this requires us to solve a Poisson equation for pressure in which all the right hand terms are known in the explicit way, and once we have that, we have to evaluate of course the gradients in a consistent way. So the discretization of all these terms has to be done in a proper way that we do not get instability and lack of consistency and all that. Okay, so then we have these equations, and here this is an explicit equation. We have 3 equations, and you can evaluate rho u, rho v, rho w, and then at n plus 1, and then use those things to come back and evaluate p n plus 1 and so on. So this is an explicit method, and this way we can look at how u, v, w and p evolve as a function of x, y, z and t. And we note here this is the overall method. In this we have not made any assumptions about either 2 dimensionality or compressibility or any such thing. We are just evaluating them in such a way that we are solving equation A and equation B. Where are we solving equation A? In the discretized form in equation D to get ui n plus 1. And how are we solving equation B? Here we are putting it in a discretized form here in order to get the pressure field. So the pressure field is seen here as a continuity enforcing variable. Okay. In incompressible flow, pressure has no significance, whether it is 100 bar or 1 bar or 0.1 bar, it is the same. The flow only reacts to pressure gradients, pressure variation, and from one point to another point, okay, the spatial velocity gradients. It does not react to the absolute value of the pressure. The pressure has no influence on the properties, okay, except outside the calculation domain. Okay, so you may have to evaluate the correct value of mu and rho at a particular pressure, but during the flow, because of the pressure variation, we do not have a variation of mu of density, and that is understanding of this. So that density and pressure relation is taken out, and pressure comes as a fictitious variable in enforcing continuity, and that is what we have done here. Okay, so we have evaluated the pressure in such a way that continuity equation is satisfied for the velocity field at n plus 1. So this is a pressure equation approach, pressure equation method for the solution of the Navier-Stokes equations. We have looked at an explicit method, and explicit method especially for coupled equations is obviously restricted to very small time steps. So you can have you would like to have an implicit method. If you want to have an implicit method, then here you will have n plus 1 and n plus 1 and n plus 1. Okay, so that makes you have n plus 1 here. This is still there. This will be n plus 1, and then this will be n plus 1, and this will be n plus 1. So we have to solve this in the we can write down the corresponding implicit version. We will leave this for the time being. Okay, so we have, this is the equation G prime that has to be solved along with D prime, in which we will have n plus 1 here, n plus 1 here, and n plus 1 here. So in order to solve this equation, we need to know pressure at n plus 1, and in order to solve pressure at n plus 1 we need to know ui at n plus 1. So that makes it difficult, so it becomes an implicit solution. So that means that as you go from time t equal to n plus 1, first of all you have nonlinearity, so you have to linearize some of the terms that appear here, and then you have to start with some guess value maybe from the previous iteration and then use that here using maybe n star, and using the n star you get a p star, okay, at and you supply the p star here, and you can maybe take some of these things onto the right hand side, and then you will be able to get a new value of velocity and use the new value of velocity here to reevaluate the right hand side. That will give you a new value of pressure here, and again put the pressure and the new value of velocities that you have got to get another value of velocity. So in that way we have to solve iteratively many times g prime and the corresponding d prime in order to get a velocity field and pressure field which satisfies both this equation and this equation. Okay, when we do that, then we have an implicit method which probably allows us to take much longer time steps than an explicit method, but one can see that it is also more complicated because at each time step we have to solve this equation and this equation several times. Firstly with un to get a p star, and then we substitute here to get ui n plus 1 star, and then we put that value here and then get this, and then we have to keep on doing this iteration several times until we get convergence. And so there is more work to be done if you are using an implicit method for this, but the advantage that you gain is that you can take longer time step than what is possible with an explicit method. How much longer and whether the additional work that you have to do for the solution of these equations is worth it depends on the factors that on many factors, including what methods we use for solution of this and this, because this is a Poisson equation. So this will be converted into, for example, AP equal to B, okay, and in several solutions of this A here remains the same because it is only the right hand side that is changing. Okay, so in such a case when you want to solve AP equal to B several times in which A matrix is not changed, then maybe we can do it more efficiently by using something like an LU decomposition method or something, where once we convert this A into some either diagonal matrix or lower triangular matrix like that, then the solution, further iterative solution of this will become easier. Okay, so we can reduce the computational time required for the repeated solution by taking specific advantage of the nature of this equation and what we are altering in this. Okay. If you look at this equation here in an implicit way, if we are treating this in a fully implicit way, we have to bring this onto the left hand side, and we have to bring this also onto the left hand side, and this goes to the right hand side. So when you look at from one equation to other equation, this term will not change, this term will change, and both these terms will change. So because of this, the matrix corresponding to this will be changing from iteration to iteration, but the matrix corresponding to this will not change from iteration to iteration because the left hand side is fixed, it is only the right hand side that is being changed. So the solution of this is probably can be done more efficiently for repeated calculations, whereas here we may have to do recalculate the corresponding coefficient matrix in solving this. But having said that, typically this equation will probably be much more difficult to converge than equation and than this equation, which is a convection diffusion type of equation. So one has to really try out and see whether the computational overhead that is required for an implicit method is really worth the additional large time step that is made possible in an implicit method as compared to explicit method. What we would like to point out is that when we use an explicit method, then we solve, in order to go from n to n plus 1, we solve equation G once. Okay, when we say equation G, this is the Poisson equation for known velocities on okay, for known velocities here. So this is this matrix equation we solve using direct methods or iterative methods, but we solve it to get Pn. Once we do that, you can go to equation D here in the explicit form like this, and the solution is very straightforward. We have 3 equations and these are, all of them are explicit, so we can, the equation is very straightforward. So the solution, that effort that is needed to go from nth time step to n plus 1th time step, where from un and Pn we get to ui n plus 1 and Pn plus 1, we need to solve one Poisson equation and 3 explicit equations. The computational effort for this is very negligible compared to this, whereas in an implicit method we have to solve this as au n plus 1 equal to, okay, a prime u n plus 1 equal to b prime, and we have to solve ap n plus 1 equal to b. We have to solve this several times, we have to solve this several times, and in the process of solving, a does not change from iteration to iteration, but a prime will change because you have some non-linearities and coupling terms which appear in this. So this equation is will require us to update the values of a prime every time. So some methods which give us an efficient solution for repeated solution of au equal to b cannot be used in this. Okay, so the overall effort that is needed to implement an implicit method is much more than in the case of explicit method, but the Navier-Stokes equations are coupled equations, in the sense that if you want to solve the x momentum equation, you also have to know V and W, and we also have this pressure business that is coming into picture. So the overall solution is quite non-trivial. Okay, so that means that the time step that may be possible in an explicit method may be quite small. Okay, so there is every advantage in going to an implicit method, but one has to see what kind of computer program skills that we have to get the best out of methods for the solution of these type of equations and these type of equations. Once we do that, an implicit method is preferable to an explicit method. So this overall pressure equation method is solving the momentum equation like this, and the continuity equation is being used in deriving a pressure equation, okay, a pressure which will enable the velocity at n plus 1th time step to be satisfied with the known values of u and p. Okay, so that's the pressure equation method. It can be applied for time accurate solution of UVPW. That when we say time accurate, that means that where we want to get the correct variation of UVPW with time. Okay, so that kind of time accurate things, it can be used for 3 dimensions, and we are not invoking any kind of compressibility effect that comes into the specification of the time step limitation here. Okay, so the time step limitation is associated with the scalar convection diffusion equation. So that means there is a component from the Courant number and there is a component from the diffusion parameter, the diffusivity, which together determine the the time step limitation in the case of an explicit method. In the case of an implicit method, because we are solving this with constant and specified coefficients, there should not be any time step limitation, but because of ui uj kind of terms where you need to know the velocities of the other components in the solution of x momentum or y momentum, there that brings in some possibility of instability. So we can use large time step but not very large time steps. So this method is possible and it is quite used. There are other methods. We will discuss one more method which has become almost the standard method for the solution of incompressible flow equations, especially in problems related to process industry where you are looking at flows inside ducts and those kind of things. For internal flows, that has become very popular, in which essentially the same idea is used. Okay, the same idea, that is, we have a discretized equation and we have a continuity equation where pressure does not appear, but we reformulate the continuity equation in such a way that correct pressure field is obtained, and by correct pressure field we mean that pressure field which when substituted into the momentum equation will enable us to get the correct velocity field, or the correct velocity field which will satisfy the continuity equation. So that kind of approach is used, and where we are solving not directly for the pressure but we are solving for the pressure correction. And what we mean by pressure correction is that with a guess pressure field we can get a velocity field from the momentum equation. Okay, so that velocity field need not necessarily satisfy the continuity equation, because in solving this with a guess pressure field, and for example using an implicit method here, we have not enforced continuity, we have not used the continuity equation or condition at any stage. So having gotten guessed an estimated velocity field from a guess pressure field, we now want to make a correction to the guess in such a way that we get an improved pressure which will give us a more correct solution which will satisfy the continuity equation. So from the discrepancy between the exact velocity field which satisfies the continuity equation and the estimated velocity field from the momentum equation with the guessed pressure field, okay, so that discrepancy is used to derive a pressure correction which will be used to update or improve the guessed pressure field to get a new value. So we will be essentially solving for the pressure correction, and that correction is incorporated in successive updates of the pressure and velocity field in much the same way as what we have been talking about here, and that method is proposed in late 60s early 70s by Partankar and Spalding, developed at Imperial College in London, and that has become very widely popular, and we will discuss that method, and it is proved very robust for a large number of equations, and so we look at that particular thing.